Okay, so this first one here says, is the function continuous at x equal to 3? And then the second one says, find the values that will make it differentiable. So let's first tackle our continuity. Revisiting the land of pre-calc. Hopefully it was a good year for you. If not, sorry. Alright, so is the function continuous at x equal to 3? Well, let's recap for the millionth time what it means to be continuous. So in order for f of x to be continuous at a point, what's the first thing we have to have? Good, f of x exists. So for this one, since we're looking at c, f of c exists. Secondly, what must we have? Okay, so the limit as x approaches c of f of x also exists. Now, little subgroup, parentheses, whatever you want to call it here. Sub idea is that means we must have my left-hand limit must equal my right-hand limit. Notice proper notation, limit of some function. We don't write limit equals limit. All right, and then lastly, what do we need to have? That they equal each other. F of c equals our limit. Now, particularly when we are working with piecewise functions, as we talked about before, you have to specify which piece you are working with. Let's go back to this. All right, so is it continuous at x equal to 3? So let's go through our steps. First of all, does f of 3 exist? Yeah, what is f of 3? Good, so f of 3 is 10 times 3 minus 1, which is 29. Awesome. All right. Now again, piecewise, we don't have the same overall limit because we have a different function coming from the left and a different function coming from the right. Now, if this was one of those ones where it did something like this, then I would be using the same function for both my left and right hand limits, so the same function for my overall. Because it's the same function whether we're coming from the left or from the right. But here we have different functions depending on whether we're coming from the left or from the right, so we do need to specify what piece we're using. Even here we should specify which piece, but we could jump to our overall limit for that one. Here, not so much. Alright, so first need check. My limit as x approaches, we're doing 3, from the left. Does that equal my limit from the right? And again, you could go ahead and write each one and then compare them. Putting that little question mark over the equal sign is fine though. Alright, so left hand, I'm using 4x minus 2x. So limit as x approaches 3 from the left of 4x squared minus 2x. Does this equal the limit from the right? And from the right, oh, so easy. Limit as x approaches 3 from the right, 30. Now again, you must specify which part. If you don't believe me, look at some AP for responses and you'll see that they require you to do that. But trust me, you need to specify which branch you're talking about. So now when I take my limit here, I just simply substitute in. So this would be, let's see, 4 times 9 minus 2 times 3. We're checking if that equals this guy here. So that's just 30. Do we agree that that's just 30? Okay. And what did we get over here? 30. Oh, how nice. So this showed us then what my overall limit is. Okay, so 1 works, 2 works. Does 3 work? No, and that's my issue. So check. We say that f of 3 does not equal my limit. This approaches 3. Therefore, f of x is not continuous. At x equal to 3. Really, anytime they ask you about continuity, you need to go through those 3 steps until you find an issue.
Wait, why would you not continue?
So in order for my function to be continuous at that point, my function has to exist there, my limit has to exist there, but then the third requirement is that they equal each other. My function value is only 29. Almost 30. Close, but what they say, close only counts in horseshoes and memory, something like that. You guys heard that before?
Yeah, it counts in everything for this.
Alright, any questions on this? Are we good on this? When I ask about continuity, you're going to show me all 3 steps, and if it's a piecewise, you're going to show me what piece we're working with, right? Labeled properly with our limit notation, because limits don't go away, they keep coming back all year. Good? Okay. So now our next problem was a continuation of what we did 2 classes ago, dealing with that differentiability. And differentiability is just simply I can take the derivative at that point. So differentiable ever means I can take the derivative at every single point. Now, in order for a function to be differentiable, we know that our original function needs to be continuous. And we talked about that we can also extend this, that if it's differentiable, that means that my original function is continuous. And also my derivative is continuous. Because think about what it means if my derivative is continuous. Continuity means the value exists, my limit equals that value. Well, for continuity, if those are the things that need to happen, and my derivative is continuous, that means the derivative is defined everywhere, and it means that left hand and right hand is the same everywhere. We talked about how another way we can look at this is that my left hand, see from the left, of my derivative is equal to the right. And again, before we knew our derivative rules, we would have had to have done the limit definition of the derivative, f of x minus f of a over x minus a, or the h1. But now that we know how to take derivatives, we can actually find our derivative and then just check to see if it's continuous there. So first, in order for a piecewise to be differentiable, we need to be continuous, and then check that its derivative is continuous. So let's go ahead and first check our original function being continuous. Now, piecewise, we see it is defined here, but we need the left and the right to be the same again. So again, for my original function to be continuous, I'm going to need my limit as x approaches 2 from the left is equal to my limit as x approaches 2 from the right. This is what we want. All right, we want that to happen. Now, we before had said this piece we want to equal this piece at x equals 2. You have to specify where. This goes ahead and specifies where right away. This is probably a better notation for it. All right. Now my left hand is going to be this guy. So I want the limit. Here's my forward. I want the limit as x approaches 2 from the left. My left piece is x squared to equal my limit as x approaches 2 from the right, and my right piece is the mx plus b. Alright, so let's actually find these limits. Take 2, put it in, we get 4 over here. Take 2 and put it in, and we get 2m plus b. Raise your hand if you at least got to this point on your warm-up. Good. Alright, so can we go any further? Do we know what m and b are, or anything more about them? Nope. So let's go and take a look at my derivative. So my derivative, again, we take the derivative of each piece. Be mindful of our intervals. Derivative of x squared, 2x. I'm going to keep that same interval, but not have the or equal to yet. And then derivative of mx plus b. What's my derivative of that? Just m, right? X is my only variable. So if I reduce my power by 1, then I'd have x is 3 power, which is just 1. And supposed to be when x is greater than 2. Okay, so we want our original function to be continuous, and we want our derivative to be continuous. So over here, then, what we want is, again, the left-hand and right-hand limits, but we want it of my derivative now. So I want the limit as x approaches 2 from the left of my derivative to equal the limit as x approaches 2 from the right of the derivative. Gotta be careful. Some of us are writing f of x rather than prime of x when we should write f prime of x. Definitely different things there. Alright, and again, we have to specify which piece we're talking about. X approaches 2 from the left. My left piece is 2s. And my right piece is just n. So here, when I do direct substitution, I get 4 plus n. Do we agree there? Raise your hand if you got to that point. Alright. Well, now that I know that n is 4, what do I need to do with that to find my b value? I just put it over here. Now, we were fortunate that for this one, we got an actual value for m. Sometimes it's another expression in which you have to do substitution. So then we get 4 equals 2 times 4 plus b. We get b equals negative 4. Alright, so for it to be differentiable, my original function needs to be continuous. So this is us trying to find f of x. Continuous. And we want our derivative to be continuous. So here is where I'm trying to find f prime of x. It's continuous. Again, for continuity, that left-hand and right-hand limits must be the same. Now that we've made this all nice and neat, we know that we can solve for an m and b value to make that derivative continuous. We'll then slack that or equals on there. Okay. Now they can ask this in a variety of different ways. This is a typical one they like to ask. Sometimes they use k. They sometimes will give you a function and say, is it continuous at the point? Is it differentiable at the point? Neither or both. They might just simply ask you to find the derivative. And you, again, need to check that point in question. But again, in practice, is what's huge is not just knowing what a derivative is, but being able to apply it. Not just knowing how to find the derivative, but knowing what it means to be differentiable, what that means for us. All right, any questions on that? Okay. So what we're going to be doing today is implicit differentiation. Has anyone heard those words before? Oh, you are in for a treat. All right, so implicit differentiation. This is a really helpful tool when we have kind of complicated problems, particularly ones that are not written out explicitly for us. But sometimes it's even helpful even when we can have an explicit function. Yes. How did you know that's what's on my post-it? Okay. Here's the state. If I implicit differentiation. Well, before was a quiz, sorry. Yeah. But you're right, it's the fourth day of notes. I love implicit differentiation. I think it's so cool. Thanks. I thought it was too quick. It's Kappa's. The words are 5 times as long. Differentiation. Okay, implicit differentiation. Notice the word differentiate. So we're still doing the derivative, but we're doing this of a function that is an implicit function as opposed to explicit. So let's talk about what those are. So we have explicit functions. And we have implicit functions. Majority of your life you've dealt with explicit functions. And basically the easy way to say this is it's in the term y, or it's in the form y equals. It's already explicitly solved for one of your variables. Alright, so explicit is one variable. is expressed explicitly, meaning that it's not expressed explicitly in terms of another variable, so there's only one other variable. Alright, so explicitly in terms of again, this is mainly what you work with. We might have y equals 2x plus 3. I could say y equals 5 e to the x minus 4. It doesn't even always have to be y, but that's what we most commonly see. Now, implicit is where we have a relation between two variables. This is just a relation between two variables. Really could be more than just two. But this is where one is not solved for the other. So you dealt with this a little bit in geometry, and then in Algebra 2 honors, perhaps again in pre-calc. But probably one of the most recognizable examples would be x squared plus y squared equals 1. What is that? A circle. So this is an implicit function because it's not explicitly solved for just one variable. It's not one variable in terms of one other variable. Now we could go ahead and solve for this. We could rewrite this as y squared equals 1 minus x squared, and y equals plus or minus the square root of 1 minus x squared. Alright, so those we could write as the same.
So would it count as explicit if the variable is squared or turn something to it as long as it's not on the same side as the other variable?
Technically still an implicit one because you want to have the variable completely. But you can actually use implicit differentiation on this guy, that guy. You can use it. Alright, now this was nice, where we could actually solve for y. But sometimes we get functions in which it's not so easy to do that. Let's say, for example, x cubed plus y cubed equals, I believe it says cosine of xy. That one's not so easy to get y by itself. You guys have any idea how we might do this? But we could break this up using our sum identity, but then we'd still have a y inside our cosine, so we'd have a y cubed and cosine of y, so we'd have to do inverse get rid of the cosine, but then we had inverse cosine of that, so that gets stuck inside. So ones like this, it's not so easy to solve for that y and to then take the derivative. So implicit differentiation allows us to take the derivative of something in this implicit format a lot more easily than solving for it. Alright, so let's go ahead and take a look. Well, let's write out the process for implicit differentiation, and then we'll go ahead and do some problems. So again, implicit differentiation is just differentiating, meaning taking the derivative of an implicit function. So taking the derivative of this guy, or taking the derivative of this guy. Although we won't do that one yet because you guys don't know the derivative of cosine yet. So again, implicit differentiation allows us to differentiate or take the derivative of an implicit function. So your first thing you want to do is to take the derivative with respect to x on both sides. So take the derivative of both sides. With respect to x.
In y with respect to x.
So it means x is what we're taking the derivative of. So let's go with y equals 3x squared. This, the derivative of y, dy dx. Meaning x is my variable that I'm taking the derivative of, the variable that I'm using. So this would be 6x. Now, if I had, let's say, 3x squared times u, and maybe u is, we don't necessarily know what the function is. Maybe it is in terms of x, we don't know. What we would have to do here is chain rule, and so I would have then, okay, let's redo this guy. So I'd have second times derivative first, which is 6x, 6x, plus first times second. This would be du dx. So I would have to take whatever u is and take the derivative of that, where x is my variable. Does that make a little bit more sense? Also, too, if this were just a constant, it would just come along for the right, just like my 3 does there. But it's basically what variable are we taking the derivative of within my equation. That makes more sense.
The explicit derivative. And then we just sort of leave it in derivative terms for the other variables.
You'll see. Yes, yeah. We're gonna be doing some stuff like this here. Yeah. Okay, so we're gonna take the derivative of both sides with respect to x, so we'll see that dy dx. And so that's kind of our thing with this, is anytime you take the derivative of y, make sure you write dy dx. So make sure you write dy dx. When differentiating or taking the derivative, so when differentiating y or taking the derivative of y, whether it's y squared, y cubed, y to the 8th power, we need to make sure we have that dy dx. This really what this does is it comes from our chain rule. We'll talk about that in a moment. So what that means then is, as I was telling Amelia, is that when we take our derivative, a lot of times we might have a few dy dx's sprinkled throughout. So then, if we're trying to take a derivative, we're trying to solve for dy dx. So what we'll want to do then is gather all of our dy dx's on one side, everything else on the other side. Okay, so then next, you guys are going to use the word gather. That sounds like a very non-mathematical term. Ooh, I didn't capitalize it. Gather. So if you've got to add some stuff to the other side, subtract some stuff, do that. To gather your dy dx's, dy dx is plural on one side, everything else on the other. And then you'll solve for dy dx. A lot of times this means divide, or like factor out your dy dx and then divide by that chunk there. So we'll take a look at a few different cases. So we'll solve for dy dx. Get it alone. Yeah. Now, we'll probably stick with writing dy dx because it lets us know we're doing with respect to x. And guys, in general, our problems that we're going to be doing, what we're assuming is that it's an implicit function where x is my independent variable, meaning that when we take the derivative, we're going to be doing it with respect to x. They could ask you to take it with respect to something else. That's why they would have to specify that. Okay, so now let's talk about why this chain, where the chain rule kind of comes into play, where it comes from with our chain rule. So this is just kind of a side note extension with our chain rule. We talked about how our chain rule is when we're doing the composition of functions, which means we have a function inside a function. And we said we take the derivative of the outside, inside stays the same, times the derivative of my inside. What we technically did here was the derivative of f with respect to g, where g was that variable, if you would, that stayed the same. Then we had to multiply by the derivative of my inside with respect to x. So kind of another way to think of this is, let me let's say that y equals f of, we use u and v a lot, let's say f of v, okay? And we know that v is some function of x, so we'll just call it g of x. Okay, so it's kind of another way of rewriting f of v, and v is just g of x, okay? So it's another way to write that composition. When I go to do my derivative, essentially what we're doing is the derivative, we're doing the derivative of f with respect to v, meaning that v is just staying there, that's my inside, times the derivative of my inside, derivative v with respect to x, okay? So my chain rule says, all right, well, if my function doesn't currently have the variable I'm looking for right there as I see it, but I know it is a function of that variable, it's a function of x, I need to then multiply by the derivative of the inside, multiply by the derivative of my inside of which it is with respect to x. So as we do an implicit differentiation problem, for example here, if I were to do my derivative of y cubed, but we want to do it with respect to x, we would follow my power rule, bring down the 3, y squared, but then we'd have to multiply by the derivative of the inside, and my inside is y, derivative of y would be dy dx. So that's where dy dx is coming from. Let's just go ahead and do a couple so you can get the feel for it. Let's start off with this one. Y squared minus 2y plus 3x equals x squared. And again, what we're going to do is find dy dx. We don't have to actually move anything right now. This is when we're being kind of hard to solve for y, because I could factor out a y here. I can subtract my 3x over factor out a y. Then I'd have y times y minus 2 equals x squared minus 3x. Still how do you solve for that? We're trying to get y by itself. So what we do is, again, we go ahead and just take the derivative of both sides of my equation with respect to x. So technically what we're doing here is we're taking the derivative with respect to x of my left side. And we're taking the derivative with respect to x of my right side. Okay, so the derivative of this big hunkin' thing with respect to x, and the derivative of this thing with respect to x. Alright, so let's go ahead and do the right side, because that's a little easier. What's the derivative of x squared? 2x. And technically what we did is we did the derivative of x with respect to x. Now, this, we can kind of think of it in principle as a quotient. Now, it's technically not a quotient in terms of the differentials, but we can think of it in terms of a quotient. So when you have something divided by itself, what is that? 1. Right, so it's just 1. That's why we don't write dx dx, because that's kind of pointless. So we know the change in x over the change in x is going to be, if it's change in the same variable, it's going to be that same value, it's just 1. So all along when we've been doing our derivatives, technically it's been dx dx, but we don't really need to write that. Now over here on the left side, we're going to first do the derivative of y squared. So you do the derivative like normal. What type of rule am I going to have to use for y squared? Power rule. So we're going to bring down our 2. Inside stays the same. Reduce my power by 1, so just 1. And again, since this is not x, I have to multiply by the derivative of the inside. Well, what's the derivative of y with respect to x? dy dx. In layman's terms, whenever you take the derivative of y, write dy dx. Okay, now the same thing for my next piece. What's the derivative of negative 2y? We were just using y as my variable that I was working with. Negative 2. But we're not taking it with respect to y, we're taking it with respect to x. So then by chain rule, we'd have to multiply by dy dx. That derivative of the inside, if you will. Okay. Derivative of 3x, 3. Now again, we took the derivative of x with respect to x, so we don't need to write out that weird stuff. That's just to let you know that I did think it's going to take Okay. So again, you take the derivative like normal, but anytime you take that derivative of a y, we have to write dy dx. Because of the chain rule, my inside is in terms of y, so I'm taking the derivative of this with respect to y, where I use y as my variable, but then by chain rule, I have to multiply by the derivative of the inside. So in short, you take the derivative of y times y. Okay, so we see that we have, I'm going to go and get rid of this so that it doesn't confuse us. We see we have a dy dx here and a dy dx here. That's what we're trying to solve for. So let's go and keep any dy dx terms on the left, move everything else to the right. What do I need to move over? Alright, so I have 2y dy dx minus 2 dy dx equals 2x minus 3. We're good so far? Now it's just algebraic manipulations and fancy footwork with their algebra skills. How can I get dy dx to be one entity, to be alone? What can I do? Yeah, factor it out. They have this in common. I want to have dy dx all together. So I have left then 2y minus 2 equals 2x minus 3. Again, we're trying to find our derivative, so we're trying to get that dy dx all by itself. What do we do now? Just divide. So dy dx is 2x minus 3 over 2y minus 2. And that's your derivative. You'll notice a lot of times with implicit differentiation, your derivative is still in terms of y and x. That's my derivative. Now from this we can see probably a restriction. We're not going to ever have y be 1. Is that right? So we could even find out what xi would make y1 if we put 1 in for y and solve for x. But that's really all it is. You take your derivative like normal, but anytime you have a y, you have to write dy dx using that chain. Questions with that?
So if we're taking derivative y per derivative of x, and we want to take, for instance, the derivative of x squared, we don't have to use a chain rule because it's in the terms we want. Right?
Yes. And that's why when specifying with respect to determines whether or not you have to specify. Okay, that's exactly right. Other questions with this? Now again, I trust that you guys know algebra. I trust that you guys can do a little bit more within your steps. So, for example, if you want to go from here to here to here, where you subtract over and factor it out, I trust that you guys can handle that. If you need to do each step, that's fine, but I know that you guys can handle some extra algebra. Okay, let's try now. I think you guys can figure this. X squared plus xy plus y squared equals 1. Again, find dy dx. So x squared plus x times y plus y squared equals 1. Again, it's not going to be easy to solve for that y. So it should be screaming at you, implicit differentiation. And again, you can use implicit just on a normal explicit function. So when you take that derivative of y, you would write dy dx. Alright, what is my derivative of x squared? 2x. Ooh, lucky us. What are we gonna do? Product rule, right? We have two entities multiply together. Alright, so product rule, we've got first and second. So my product rule, reminders. Second times derivative of first plus first times derivative of the second. Okay? So second times derivative of first. What is the derivative of x? 1. We didn't really need to write that, but so be it. Plus first times derivative of second. What's the derivative of y? 1 dy dx. Remember, derivative of y is just dy dx. Alright, that wasn't that exciting with product rule because it's already over. Alright, now, derivative of y squared? 2y dx. And what is the derivative of 1? 0. Again, we want dy dx is on one side, everything else on the other. Can we handle factoring it out and moving stuff? Okay. If you don't see what I'm doing, you know. So dy dx comes out and I have left an x and a 2y. So I took care of those guys. And I'm going to subtract over negative 2x and minus 1. Questions on what we did there? We did a little bit.
Wait, where'd you get that x from?
This x. So I moved this guy and this guy to the right. So I subtracted them both to the other side. And then here I factored out by dx.
So then where'd you get that x from that x plus 2 1? Yeah.
So I have then took away those guys. I've left this and this.
Oh,
So I factored out by dx. Other questions before we move on? Okay, so then we just go and solve for dy dx. Do we agree with that? That's my derivative. Now, we have only entered into the world of limits, continuity, differentiability, derivatives. And we see similar types of questions keep popping up, such as write the equation of the line tangent to f of x at x equal to some number. We can still have that even with this. Let's do it with this problem. Let's continue. Let's pull this part A. And now let's do part B. So now, they're gonna, or actually they might not even start off asking about the derivative, they might just start off with that equation and say, write the equation, that's my shorthand notation for equation, write the equation of the tangent line at, let's put in tangent line at x equal to 1. Because if you think about it, our explicit functions, for example, y equals x squared, we would have passed that vertical line test, right? But then if we think of our implicits, such as x squared plus y squared equals 1, what does this create again? Circle. Does that pass that vertical line test? So if I asked you for the tangent, asked you for the tangent at, let's say, x equal to 1/2. Right there, now two different spots. We now have 2 points for x equal to 1/2, so thus we might have more than one tangent line. Not always going to be the case, but with our implicit differentiation, that might come up. Okay? So part B says write the equation of the tangent lines at x equal to 1. Equation of the tangent line. We know for the equation of any line, we're going to use point slope form. Y minus y1 equals n times x minus x1. Like, please, Mrs. Margraf, don't make us do another one. We're doing it. All right, so we need a slope and we need a point. Do I have my slope? Kind of-ish. We have an equation for my slope, right? Remember, slope of the tangent line is what? Your derivative at that point. Not enough just to be able to take it. You gotta know what it means. So my slope of the tangent line is my derivative at that point. Okay, so we've got an equation to be able to find that. So we have our point. We've got x. Do we have y? No. How do I find y? Yeah, put it back into my original equation, because we want to know where this occurs in my original. Okay, so we've got x equal to 1. Let's find y. So let's see, we've got x squared, so 1 squared plus 1 times y plus y squared equals 1. Anybody know why I'm finding my y value first before finding my slope? Take a look at that slope equation. Why do I have to find my y value first? Yeah, we need it to find my slope. I can plug in my x, but I need to have my y values. Alright, so we get 1 plus y squared equals 1. Oh. So do you agree we have y times y plus 1 equals 0? I subtract my 1s, they cancel. Bring it up for you. Subtract my 1s, they cancel. I'm left with y plus y squared equals 0. Factor out that y. Do we agree with this equation? Okay, so then I have y equals 0, and y equals... Oh, looky there! We do have 2 points. Twice the fun! Alright, so we have 2 points, which indicates 2 points at which we can have tangent lines. So this is going to be the point 1, 0, and this is going to be the point 1, negative. Alright, so we do have to find both tangents. But now we have both points, so let's go find the slopes that go with it. Alright, so my dy dx, my slope, evaluated at the point 1, 0. And this is proper notation here. You could just say at 1, 0, dy dx equals. But this is saying dy dx evaluate at 1, 0 equals. So that's proper notation there. Alright, let's put it into my function. Negative 2 times 1 minus 0 over 1 plus 2 times 0. What's that? What did we just find there? What's negative 2? Slope. Alright, so this negative 2, that's my slope for this guy. Alright. Now let's find our slope for the other one. We can write our equation right now. Let's not read about the other guy. So I need my derivative at the point 1, negative 1. Alright, so negative 2 times 1 minus a negative 1 over 1 plus 2 times negative 1. Alright, so we get plus 5, negative 2 plus 1, negative 1. 1 plus negative 2, negative 1. Do we agree with the slope of 1? I agree. Okay, and what did we just find here? Turn to your partner and tell them what we just found. Slope where specifically? At this point x equals 1. So my slope for this guy is 1. Now can we write our equations? I saw 2 hesitant yeses. Do we think we can write our equations now? Let's try it out. Alright, so my equation for this guy would be y minus 0. I mean, you don't have to write that, you could have just written y. Equals negative 2 times x minus 1. That's one of my equations of the tangent line. And for this guy here, y minus negative 1 is like plus 1 equals 1 times x minus 1. Again, you don't have to write that one. That's my other equation. Again, you're not always going to have to, just it's a possibility. You're like, great, Mrs. Margaret, I have no idea what we just did. Well, let's take a look at what this means. There's this thing called WinPlot. You can actually download this off the internet. It's really cool. Alright, so my original equation, oh look at that, implicit, was x squared, so x times x, plus x times y, plus y squared, y times y, equals 1. Any ideas as to what this might look like? No one wants to give it a shot? An ellipse! Okay, so here's my implicit function. And we were asked to find the equation of the tangent lines at x equal to 1. So if we look here, we can see we have that dot there. Right, and didn't we find that one of my y values was 0? And then we also have down here. Oh, and didn't we find that my other y value was negative 1? That wasn't too good. Okay, well, we actually have the equations of our tangent line. So let's see, my one equation. What was that? Y equals negative 2x minus 1. So y equals negative 2 times x minus 1. Boom! There's our tangent line. All right, and then my other one is this guy here, y plus 1 equals 1 times x minus 1. So y plus 1 equals y plus 1 equals x minus 1. And there's my other tangent line. And that's what we just found. So they gave us this equation. We found the derivative, which will give us the slope of the tangent line at any point along here. And then we use that to help us write the equation of the tangent lines. We found our slopes at this point. And if you think about it, my slope for this point right here, for this guy, was a slope of negative 2. Does that look like a slope of negative 2? That seems reasonable. And my slope for this point was a slope of 1. And that looks like about a slope of 1. So that's what's happening there. Alright, questions with that? I don't know how to bring it back down. So that's what we have going on. Alright, let's go and take a look. Alright, I want you guys to go and try this one on your own. Find dy dx given 2x squared y minus 4y cubed equal to 4. So x squared y minus 4y cubed equal to 4. Go ahead and find your derivative of all that. anytime you take the derivative of y. Compare your answers with someone nearby you. If you're stuck, talk with one another. If you were right and they were wrong, be kind to one another. Alright, let's take a look at this. Now you go to, you're like, alright, I got this. Implicit differentiation, and as soon as you start off, you're like, oh, product. So again, just be careful, one piece at a time. I see two variables multiply together here. So second stays the same. times derivative of the first. And what's the derivative of 2x squared? 4x. Are we good so far? And plus, first stays the same, times derivative of the second. What's the derivative of y? 1 dy dx. Why did I not have to write dy dx for this guy? Right, we weren't taking the derivative, we were just taking that portion of my function. Okay, so that's my product rule. Now this part's not so bad here. Negative 4y cubed, bring down my 3, so I have negative 12y squared. But I took the derivative of a y, so we must have dy dx. Again, it's that idea that we did our power rule, and then chain rule says we multiply by the derivative of right-hand side, which is y, so dy dx. Alright, and what is the derivative of 4? 0. Stinking 0. Alright. I'm going to go subtract my 4xy over. So now I have 2x squared dy dx minus 12y squared dy dx. I'm going to factor out that dy dx. Taking this guy out. So I have dy dx. And 2x squared minus 12y squared. We good there? Okay. And then so dy dx equals negative 4xy over 2x squared minus 12y squared. We good? And then we say, oh, well, we can cancel one of those, and we can cancel that guy, and this is actually negative 4 over 2x minus 12y. No, we cannot do that. No, 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 no. We cannot just simplify a little piece here with my top and a little piece here with my top there. No, no, your algebra brain should be screaming at you right now. We cannot simplify there. Is there anything I could simplify though? I do. I could reduce by a factor of 2. For response, we don't have to. But we could reduce by a factor of 2. You guys are supposed to yell at me and be like, Miss Markup, you're lying to us. Only within reason. Questions on that? You might jump on that one. Alright. Let's take a look at how they might change this up. How would they put this into multiple choice format? Or this actually, they might churn into a multiple choice type. Alright, so let's start off with a fairly innocent equation. Given x squared plus y squared equals 1. Show that my second derivative is equal to negative 1 over y cubed. Now this could be phrased differently. It could just say find dy, or find the second derivative. In multiple choice, they might just say find the second derivative, but their multiple choice answers would include this guy here. Alright, so let's just go and do this like normal. You find your first derivative, I'll find my first derivative, solve for dy dx, and see if we get the same thing. You go first, I'll give you the answer. We get our first derivative simplifies down to negative x over 1. Okay. Now let's find our second derivative. Oh, glory be, we get to do quotient rule. Alright, so d squared y over dx squared. Alright, quotient rule. Take it one piece at a time. We're working with this guy here. Okay. So bottom stays times derivative of the top. What's the derivative of negative x? Minus top stays times derivative of bottom. What is the derivative of y? dy dx. Don't forget your denominator. All over, what do we have there? X squared, the bottom squared. What do you want?
Like, because we have to solve for dy dx, so we make it equals.
We're trying to find our second derivative. So our second derivative equals this. But our second derivative is not only in terms of x and y, but there's a statement dy dx. Now let's clean it up a little bit. Do you have a
Wait, so what is the y was? Like, how did the y
so my quotient.
I know it's a quotient rule, but like,
So bottom times derivative of the top minus top times derivative of the bottom squared. Okay, so it was bottom stayed.
yeah.
Derivative of top. Oh, this should be a negative.
Yeah,
That's
what I
interesting.
was gonna say.
I'm sorry. We even said negative one, right? Thank you.
I was like, why isn't it negative one? I didn't know.
It is. It was just late in getting there.
Yeah.
Thank you. Okay, now that just looks fine. Are we good now? Thank you. Okay, so let's clean it up a bit. Negative y plus x dy dx. Y squared. Do we agree with that, Peter? Now, we can't leave it like this where it is in terms of dy dx. What can I do to get rid of dy dx? Easier than that? We already found it! We know what dy dx is, right? It's this guy. So can't I just substitute that in for dy dx? Ah. So negative y plus x times negative x y. And you're like, great, now we've got a complex fraction. That's not any nicer. Alright, so we are going to have to simplify from here. Oh, my fractions are going a little sideways. A little lopsided. Alright, so let's see. We're going to need to have common denominator on top. Okay. I'm going to try to write more straight this time. So would you agree we get to multiply by y over y? And then we have negative x. So here I'm just trying to get a common denominator. Again, for your spots, we cannot have that complex fraction in there. So let's get rid of our complex fraction. We could have stopped, but we're trying to get it to what they told us it should be, negative 1 over y. Alright, so let's see. Over here we get negative y squared over y plus negative x squared. So let's just go. Let's go ahead and combine that together. So I get negative y squared over y, negative x squared over y. So let's see, negative y squared minus x squared over y. Do we agree with that? I'll let you write down what's over there. Perhaps what it would have been a little faster is if we would have done what we talked about a couple classes ago. Can we have just from right here multiplied by y on top and y on the bottom? Remember how we did that? That probably would have been faster. That's all right. We'll get there. Alright, what does this down here simplify down to? I'm running out of space. Can we just think of this as negative y squared minus x squared over y times 1 over y squared, right? Because we have to do the reciprocal. Also, I think some of your teachers might have reminded you that if it's being divided here, we can just divide those together. But all that to say that we get negative y squared minus x squared over y cubed. Are we good there? Okay, well, we got a y cubed in the bottom, but on top, how in the world did they get a negative 1? What's that? Okay, we need to get this closer to the top. Oh, so close. Gee, our given says x squared plus y squared equals what? We are so close to that. Take a look at this guy here. It's close, but not quite. Couldn't we factor out a negative 1? Right? And what does this guy equal? 1! Oh my goodness, they weren't lying to us. So I'm sorry I did the bad math there without labeling everything. Oh my goodness, thank you. That is cubed. Cubed. And looky there, they weren't lying to us. Isn't that nice? That's the type of thing they might make you do on multiple choice, in which they wouldn't have any of these answers as your answer. No, they would make this your answer. Okay, so you'll see that anytime they ask you to find your second derivative, you do have to go ahead and replace this dy dx. Now, in terms of response, again, once you get rid of that thing there, you don't have to keep simplifying. But do look to see if you can simplify using your original as well. Okay, questions on that? I don't know about you, but I feel exhilarated after that. Let's go ahead. Yeah, let's do this. I know that one, especially because those fractions are taking us up so much more. Okay. Let's see, we've done product rule, we've done quotient rule, let's throw something else out.
It doesn't be simple.
Yeah, it's not too bad. Trying to squeeze it on your paper. Oh, sorry. Find you, I did this. Given that x equals the square root of x squared plus y squared. And does the square root of x squared plus y squared give us just x plus y? No. You guys make me die 5 years earlier each time I see that. How many times I've seen it? I don't think I have much time left on this one. Alright, let's rewrite this. What does that hint to us we're going to have to use? Yeah. Alright, so doing our derivative. Derivative of x is just 1. Now when we do our chain rule here, we go and drop the 1/2. Inside stays the same. Reduce the power by 1. Multiply by the derivative of the inside. So we don't have any dy dx's yet, because I haven't taken the derivative of a y chunk. But I'm about to. So multiply by derivative of the inside. What's the derivative of x squared? 2x. And what's the derivative of y squared? 2y dy dx. Alright, I think it's a little hairy. So we want to get dy dx by itself, right? I kind of feel like maybe we should clean up so we can even see what's in the denominator, what's not, so on and so forth. Let's see. 2's in the denominator. This guy is in the denominator. He's just sitting on top. What do you guys think we can do next? Yeah, let's go ahead and multiply by my down here, if you would, cross multiply. So what we really have then is 2 times x squared plus y squared half is 2x plus 2y x. Okay, so again, we're trying to get dy dx by itself. What should we do next? Yeah, subtract 2x. Also, guys, it might be a little bit easier to also recognize. Could I divide everything by 2? Yeah, so we could do that as well. I'm going to do both in one step. Okay, so I'm going to go ahead and divide by 2, so my 2's reduced. So we have x squared plus y squared 1/2 minus x equals y divided by x. Then what do we have to do? Divide by y. I'm going to rewrite this as a square. Help us see something. But again, let's check to see if that original popped back up anywhere. What's my original? Square root of x squared plus y squared. Do I see square root of x squared plus y squared anywhere? Yeah. Oh, where do you go? Looky there. What can I replace that with? Oh. Oh, wait a second. What? What does my derivative equal? If you're able to do so. You're not always going to be able to. Amelia asked a good question. Do I always need to plug in my original? No. Look to see, is it there? Pretty simply, then if so, do so. Now, let's think about this, because you're like, what? You're 0. I don't know that I believe you. I said the same thing. Let's take a look at my original. If I were to write this explicitly, we would have, how would I get y by itself? What would I have to do first? Square both sides. And then what would I do? Subtract your x squared, right? Y squared equals 0, y equals the derivative of y equal to 0 is 0.
Can we have a little bit extra back there?
Like up here? Or up here?
Yeah.
Yeah, you could have, anywhere where you see that square root of x squared plus y squared, you could have substituted that.
And we're about the same answer.
Yep. Alright. You probably won't ever see that again. I mean, you might, but that's just. Alright, let's finish. The answer's not 0.
It's 4 minutes left.
Oh, good. It'll only take it 3. It might take you more than 1.
I'm hungry for it. It's DY.
Thank you.
It's an offer.
I have written next to it, doozy.
Wow.
It's a bit of a doozy.
Wait, in a good way or a bad way?
Your definition of good way or my definition?
Which I agree.
Thank you.
Where is it? I just know that.
They're all graded, but I'm going through and doing the spreadsheet for should be good.
Pardon the interruptions, ordinance. We just have a few afternoon announcements. Interact will not be meeting today. Instead, Interact will meet next Tuesday, October 10th. Also, the deadline for the applications have also been extended to October 10th.
Fun.
If you are a junior or a senior with a 3.5 cumulative GPA or above, you are eligible to apply and to be inducted into the National Honor Society. Current members do not need to reapply. Check your Blackboard site for directions.